Let's talk about some important Taylor series that come up quite a bit and are really nice to show. So, the first one is for sine of x. So like before, let's figure out the derivatives and then use that knowledge to be able to build our Taylor series. So we know the derivatives for sine alternate sine, cos, negative cos, and that repeats in that grouping of 4 over and over again for infinitely long. And let's say we want to center our Taylor series at 0. So let's say this is indeed a Maclaurin series. Well, we fill in 0. So f of 0 is 0. The derivative at 0 is 1. The second derivative at 0 is 0. The third derivative at 0 is -1. And this pattern will repeat. It'll go 0, 1, 0, -1, 0, 1, 0, -1, infinitely far. So we kind of know from this what our terms are going to be. So let's write it out. We know that C0 is going to be 0. C1 is going to be 1 over 1 factorial times x. So that's C1 times x. Then what do we have times x squared? Well, we have the second derivative evaluated at 0, which is 0. So that term is going to disappear. I'm going to write it as 0 times x squared. Though this is like, we're thinking of this, maybe I'll write it as 0 times 2 factorial times x squared. And then we have plus -1 over 3 factorial times x cubed. Since the third derivative evaluated at 0 is -1, because remember this is a Maclaurin series, so we're centering our series at 0. And it continues like this. So we have 0 over 4 factorial x to the 4th plus 1 over 5 factorial x to the 5th, and it continues on. So now we kind of understand what's happening here. It's alternating, the coefficients are alternating 0, 1 over 1 factorial, 0, -1 over 3 factorial, 0, 1 over 5 factorial. So the only terms that are surviving are the terms that have odd degree. And it also seems that the odd degree terms are alternating positive, negative, positive. X to the 7 would be a negative term. We just need to be able to come up with a nice way of writing this. So let's think about this. Well, we only care about odd terms. So just as a quick reminder here, remember an odd number is always of the form 2 times any number plus 1. So 2n plus 1. So we're going to use that idea. We'll let I go from 0 to infinity. And now our coefficients, the ones we want to survive, the 1, the 3, the 5, the 7, we're going to write 1 as 2 times 0 plus 1, 3 as 2 times 1 plus 1, 5 as 2 times 2 plus 1. So we know here we're going to have x to the 2i plus 1. And we know our denominator in this case is going to be the same as the power of the term. So we have 3 factorial here, 3 here, 5 factorial here, 5 here. Our degree is 2i plus 1, so this is going to be 2i plus 1 factorial, because we know they match. And now we just have to make sure that we alternate positive to negative. So every term alternates, so we're going to have -1 to the n, or n plus 1. We have to just decide what works for us. So we have the first term is positive, so we want when I equals 0 for this to be positive, so we want n -1 to the 0, so we'll just have that as n. So we have here indeed a Taylor series for sine of x. So we can always use this in place of sine of x, which is fantastic. Now we just have to see the radius of convergence to see for what x just holds. So let's find the radius of convergence. So we'll use the ratio test again. That's always a good test. So it's going to be the I plus 1th term. So that's going to be x to the 2i plus 1 plus 1, which is 2i plus 3 over 2i plus 3 factorial. Remember, we're taking the absolute value here, so we're not concerned about negative 1 to the n here. And then we're going to multiply by the reciprocal of the nth term, x to the 2i plus 1 over 2i plus 1 factorial. And if we simplify that, we have 2 x's survive. So all of these go with almost all of these, but there are 2 left over. And this gets canceled out with everything but the 2i plus 3 and the 2i plus 2. So we get this is 2i plus 3 times 2i plus 2. And just by looking at this, there are no i's in the numerator. So the numerator is kind of fixed once you're given an x. And as I goes to infinity, the denominator grows. So we were pretty sure, in fact, we were 100% sure, that the limit of this guy is indeed 0. So the radius, so this always holds for any x. The limit is 0, so it always converges, because remember, as long as your ratio is less than 1, you get convergence. So we'll just say over here that the radius is indeed infinity. So this expression here holds for all x. That's fantastic. Similarly, you can show that cosine of x has a very similar Taylor series here, but the even terms are going to be the ones that survive here. So you have x to the 2n over 2n factorial. It might be a good exercise to check the same ideas from the previous example with cosine of x to make sure that you're getting the same thing here. So that's great. And there's 2 more I'll leave as examples here, or as exercises. But as long as you follow the same ideas as the previous examples, you'll be able to see these. But the arctan, or tan inverse Taylor series, is given by negative 1 to the n times x to the 2n plus 1 over 2n plus 1. Not factorial, just 2n plus 1. What you'll see is by the time you take the first derivative, you already have something of the form 1 over 1 plus x squared. So you're in a situation where if you take future derivatives, factorials will appear in the numerator, and they'll cancel off with the factorials that appear in the denominator of your coefficients term. So give that one a try. Make sure that you can indeed see that one. And similarly, ln of 1 plus x is another one that's going to behave similarly. You can imagine if you take the derivative here, you're into some sort of rational function. Then you'd get something along the lines of 1 over 1 plus x. So this one turns out to be In this case, you start at 1 to infinity, and you get negative 1 to the n minus 1 times x to the n over n. So those along with, and I'll write down e to the x as well. This isn't an exercise, but it's good to have in the same place since this is a very important one as well. This is x to the n over n factorial. Sine, cos, and these three here are Taylor series that come up all the time. And if you do see expressions like that, you can use these ideas to be able to solve some problems. One nice use of Taylor series is that you can take polynomials that are written in terms of x and rewrite them in terms of some other shifted variable. In this case, we're going to do x minus 3, but you could shift it to whatever you want. Now, the first thing to think is that, well, I know that at most, the third derivative is going to be non-zero. If I take 4 derivatives here, then you could see that I'm going to get a bunch of zeros. So in some sense, I know I only have to worry about the first 3 derivatives here. So the Taylor series is going to be finite. But that's okay. We can still use the same idea. So let's write this as a Taylor series centered at a equals 3. Okay, so we have our function f of x, and if we, well, let's just write that down, x cubed minus 10x squared plus 6, and if we plug in where we're centering it 3, we get 3 cubed 27 minus 90 plus 6, which you can check is negative 57. Our first derivative at x is going to be 3x squared minus 20x. And if we plug in 3 into our first derivative, you can check pretty easily. You see that we get 33. The second derivative, well, that's going to be 6x minus 20. Again, it's pretty easy to see if I plug in 3 in here. I'm going to get negative 2. And the third derivative at x is just going to be 6. So this is the constant function 6. So at any x value, you get 6. And the fourth derivative in any higher, so let's say I'm going to use some terrible notation, n greater than or equal to 4, the fourth derivative or higher at x is going to be 0. Okay, so that's great. So we have that our Taylor series now centered at 3. Well, since the fourth derivative and higher is 0, all of those coefficients, C4, C5, all the way up to C infinity, is going to be 0. So really, I only need to take the finite series going up to 3 here. So this is going to be f of I at 3 over I factorial times x minus 3 to the I, and I can just write this out term by term. So I have the 0th derivative evaluated as 3, which is minus 57 over 0 factorial. 0 factorial is 1. And then x minus 3 to the 0, so that's 1 as well. So the constant term is just minus 57. And then the next term is going to be, well, it's going to be the first derivative evaluated at 3, so 33 divided by 1 factorial, which is 1, times x minus 3 to the 1. And then we have the second derivative, so that's negative 2. So the second derivative evaluated at 3 is negative 2 over 2 factorial times x minus 3 squared. And then finally plus 6 over 3 factorial, our third derivative evaluated at our center 3 times x minus 3 cubed. And we can simplify this. So we can see that 3 factorial is 6, so we have 6 over 6, that's just 1. And I'll write these in descending powers. So this is going to be 1x minus 3 cubed. And then here we have negative 2 over 2 factorial, so that's going to simplify to a negative 1. So it's going to be minus x minus 3 squared, and then plus 33 x minus 3 minus 57. So we just kind of shifted this polynomial to be written in terms of x minus 3 as our variable and not x. And a Taylor series is a good way to do that. Let's do this example here. Let's find the Taylor series of this rational function, 7 over x to the 4th, centered at x equals negative 3. So again, we're going to turn some function into an infinite polynomial. It's going to be centered at x equals minus 3. So let's do what we usually do. Let's find our derivatives. So, well, f of x is just 7 over x to the 4th. And for now, let's calculate what's going on at the center at negative 3 after we work out the pattern with the derivatives. And that's what we're going to have to do here, is we're going to have to figure out what the nth derivative is going to look like. Now remember, the key for these is don't multiply things out. Leave things unmultiplied and unsimplified. See if you can notice the pattern. So the first derivative is going to be, well, we can think of this as 7. In fact, maybe I'll rewrite this as 7 times x to the negative 4. That might allow us to notice the pattern a little bit easier. So I'm just going to use the power rule here. So we're going to get 7 times, I'm going to write this as negative 4, but I'm going to write the negative 4 as negative 1 times 4 times x to the minus 5. Okay. And then I'm going to write the second derivative. Okay, so the 7 stays there. And we have this negative 1 and this 4. And then we're going to multiply by another negative 1. So that's x1 squared times 5. Again, we're multiplying by negative 5. So that's negative 1 times 5. And then x to the negative 6. Am I thinking about splitting up the negative 5 into negative 1 times 5? Is I'm thinking if I keep multiplying by negatives, it's going to alternate negative, positive, negative, positive. So it's a good idea to split out these negative ones to simplify your series that way and to kind of notice the pattern a little bit easier. Let's do a few more. The third derivative is going to be 7 times negative 1 cubed times 4 times 5 times 6 times x to the minus 7. Again, just using the power rule here. And we'll do one more. The fourth derivative of x is going to be 7 times negative 1 to the 4 times 5 times 6 times 7 times x to the minus 8. And from here, you might kind of see the pattern already. So what we have is we're not quite starting at 1. It's almost like a factorial, but we're missing some terms. But we're starting at 4, and we're going up to, in this case, 7. So if we take the fourth derivative, we go up to 7. That's 3 more than 4. If we take the third derivative, we got up to 6, which is 3 more than 3. The second derivative went up to 5. So it looks like it's almost like going up to n plus 3 factorial. We have this negative 1 to the same power as our derivative. That's great. We have this being x to the negative 1 more than this number here. This was n plus 3, so this is going to be negative n plus 4. So that looks pretty great. So let's kind of write down what we have. So the nth derivative is we have 7 times this negative 1 to the n. And then we want to go up. I'll leave some room here, but we want to go up to n plus 3 factorial. But we don't have the first few terms. We don't have a 1 times 2 times 3. So in some sense, let me kind of get rid of those in n plus 3 factorial by dividing by 1 times 2 times 3 factorial. Actually, I don't need to leave any room. Let me rewrite this a little bit closer. So it was n plus 3 factorial, and then we didn't have the first few terms. We were starting at 4, so I'm going to divide by 3 factorial here. There we go. And we have x to the negative n plus 4. So that's great. We have a nice formula. And this formula will hold for all derivatives as well. And when we plug in negative 3, so let's do it. Fn at negative 3 is going to be 7 times negative 1 to the n times this n plus 3 factorial divided by 3 factorial. But this is just some constant term that's not affected by n. I'm just going to multiply that out. 1 times 2 times 3 is 6. So I'm just going to write this as 7 over 3 factorial, or 7 over 6 here, just to make my life a little bit easier. And then this n plus 3 factorial. And we're going to multiply by negative 3 to the negative n plus 4, which I can rewrite in the following way. In fact, let me actually do it up here. So we'll say that this is 7/6 times negative 1 to the n times n plus 3 factorial. And I'm going to write this as divided by negative 3 to the n plus 4. And I'm going to rewrite this. My thought is I want to take out this negative 1 to the n plus 4 in here and cancel it with as much of these negative 1s as I can. So this is going to be 7/6 times negative 1 to the n times n plus 3 factorial over negative 1 to the n plus 4 times 3 to the n plus 4. Now you can see here that these n negative 1s are going to cancel off with these n negative 1s. And I'm left with 7/6 times this n plus 3 factorial in my numerator. And then I have negative 1 to the 4 in my denominator, and 3 times n plus 4, 3 to the n plus 4. But negative 1 to the 4, that's just 1. So I can rewrite this as 7/6 times n plus 3 factorial over 3 to the n plus 4. So that's great. This here, we just figured out, is a nice simplified version of our nth derivative evaluated at our center at negative 3. So let's plug this into our Taylor series. I'll use the index n here since I used n over on the left-hand side. So n goes from 0 to infinity of 7/6 times n plus 3 factorial over 3 to the n plus 4 divided by n factorial times x minus 3, so x plus 3, to the n. And let's cancel out as much as we can and simplify as much as we can. So I notice, first of all, I have an n factorial in the denominator and an n plus 3 factorial in the numerator. So all but n plus 1, n plus 2, and n plus 3 are going to get canceled out here. So all of these guys are going to go with all of these guys except for n plus 1, n plus 2, and n plus 3. Also, what can I do here? I can take out this plus 4, take out 4 3's and combine them down here. Maybe that's a good thing to do. So this is going to be the sum with the same indices, 7 over 6 times 3 to the 4, which is 81, times, and what do I have left over? N plus 1, n plus 2, n plus 3, and then divided by 3 to the n, which is left over, and then times x plus 3 to the n. And that's basically as simple as we can get it. Maybe we could change this. 6 times 81, we can multiply that out to 486 if we like instead. But basically this is it. And as an exercise, show that the radius convergence is just 3. So again, you can do that just via the ratio test, but that's really important to determine for which values of x this Taylor series can be used for. Otherwise, it doesn't make sense. Your x values have to be in the radius of convergence, centered at, in this case, -3. So, a few final notes here. There's one example, and you can look this up in your textbook. It is example 7 in chapter 11.10, where, especially when you're dealing with sine and cosine not centered at 0, you'll find that the derivatives kind of split up into 2 different cases of values. So you'll have to split up your Taylor series into 2 distinct parts. Have a look at that example to see what I mean there. The second thing, and this is a nice idea too, just like with power series, is you can use Taylor series that you've figured out with more complicated variables in the same way, just replacing the variable with the more complicated thing. So here we have e to the -x squared. This could be whatever you want, actually. So you have e to the -x squared. This is just going to be -x squared to the n over n factorial. Because if you remember, e to the x was x to the n over n factorial, as n goes from 0 to infinity. So that's a nice idea as well. If you have more complicated things here, you can indeed just swap it out with something that you know and come up with a nice power series representation or Taylor series for that too.